In the last video, I talked about the UNET and how it was used in the global health pandemic to scan lung x-rays. But now it's time to go behind the scenes and actually understand how the UNET works. The UNET is a type of CNN architecture that consists of an encoder, a bridge, and a decoder. And through the meshing of these layers, we get semantic segmentation where you input an image and you can get pixel by pixel masks of where the model thinks regions of interests are. Let's start simple. Imagine you have a complex photo, maybe one of an elephant, and you want a computer to figure out what's in it. Instead of analyzing every single pixel in isolation, CNNs or convolutional neural networks use special filters. You can think of these as sliding magnifying glasses that look for familiar patterns like edges or circles as they move across an image. The CNN learns which types of patterns are important for identifying different types of features or objects. Now that we know how the basic CNN works, let's go more into depth as to how the UNET works, starting with the encoder. The job of the encoder is to reduce the dimensions of the image while retaining the same amount of information. This is done through multiple convolutional layers and max pooling layers. The convolutional layers extract important features like shapes and the colors of the object, while the max pooling layers keeps only what's necessary and removes the noise. Doing this multiple times reduces the dimensions of the image, going from 224 to just 54, which can be reduced further with more convolutional layers. However, you may see that the number of channels has increased to 128. Through this encoding layer, we have now reduced the size of the image but have kept the same amount of information. This info. Why can't we just have the 224 RGB image? Well, it's simply because it's computationally inefficient and redundant, because neighboring pixels are very similar and it's really hard to comb through 150,000 pixels. Also, the raw pixels don't really tell us about the shapes and the features of the elephant, and they don't have important features in them which the neural network can learn easily. Which is why we compress it and then we give it 128 channels. What this means is that now there's 128 separate slices, but each one of them recognizes a certain part about the image, whether it be the trunk, the eyes, the shape, the size, the color. And this just makes it a lot more learnable, and it's higher quality for the neural network to process and learn these patterns. Now that we know the purpose of the encoder and how it works, let's move on to the next part of the UNET, the bridge. Here's the UNET bridge, the narrowest point where encoder output flows in. It contains convolutional layers that process the most compressed features. Watch the data flow. Features enter, get processed, and then it gets prepared and refined for the decoder. This makes sure that only the essential patterns pass through to the decoder to create the final mask. Now let's move on to the decoder, the final part of the UNET. This is where the segmentation mask is made and the spatial dimensions are unraveled. The UNET decoder starts with compressed 16 by 16 features from the bridge. Progressive upsampling expands to 32 by 32, 64 by 64, 128, and so on. Watch this upsampling in action. These smaller pixel grids become larger, more detailed representations of the image. Skip connections preserve the fine details from the encoder, adding the high resolution information back to the decoder level. The final classification assigns class probabilities to each pixel. Then argmax, which is a function, selects the winning class. As a result, we get pixel-perfect segmentation where every pixel knows exactly what it represents, whether it be the elephant or the background. So, to sum it all up, the encoder extracts features, shrinking the image and increasing the number of spatial channels at each stage. The bridge compresses the features to 16 by 16 and hands it off to the decoder, keeping only the most essential patterns. The decoder gradually upsamples the features to full resolution with the help of skip connections, which carry high-resolution details from the encoder. A final classifier appears, which is a one-by-one convolution output, for which outputs a class score for each pixel. argmax selects the final class, and the result is a segmentation mask. And if you're a real one who stuck till the end, here's a secret about UNET that no one knows about.
Psych!